Somewhere, 700 million years after the Big Bang, before Earth existed, before our sun existed, before almost anything you can name existed, there is a galaxy that is too big. Not a little too big. Not, that's odd, too big. Too big by the rules of physics as we currently understand them. And the James Webb Space Telescope found it, along with 5 others just like it. And today, in 2026, astronomers still don't have a clean answer for how they got there. Here's the setup, and I promise it's wilder than it sounds. For the last 30 years, cosmologists have used a model to describe how the universe grew up. From a hot, dense soup right after the Big Bang into the galaxies, stars, and planets we see today. That model is called Lambda CDM, or LCDM for short. Lambda stands for dark energy. CDM stands for cold, dark matter. Together, they are the 2 invisible ingredients that, according to this model, make up about 95% of everything in the universe. LCDM isn't a fringe idea. It's the mainstream textbook, "This is how the universe works" model. It's been tested for decades. It explains the leftover heat from the Big Bang. It explains how galaxies cluster together across billions of light years. It's been right again and again and again. But LCDM also makes a prediction. It tells you roughly how fast galaxies should be able to grow in the early universe. Gravity needs time to pull matter together. Stars need time to form. Galaxies need time to assemble. There's a speed limit baked into the model on how quickly a small, young universe can build something massive. And when JWST turned its infrared eyes toward the deep past, looking at galaxies from just 500 to 800 million years after the Big Bang, it found galaxies that blew straight through that speed limit. We're talking about objects that, according to the light we're receiving from them, already contain more than 10 billion times the mass of our sun. In stars, already formed, already burning. Less than 1 billion years into the history of everything. To give you a sense of scale, that's not a small galaxy. That's approaching the mass of a fully mature galaxy, sitting there in what should have been the toddler phase of the universe. The astronomer who put this most bluntly is Mike Boylan Colchin from the University of Texas at Austin. In a study published in Nature Astronomy, he looked at 6 of the earliest, most massive galaxy candidates JWST has found. His conclusion, in plain language: if the masses and the distances are both correct, these galaxies shouldn't be able to exist yet. Not under the standard model, not with the amount of time and matter available. He wasn't the only one to notice. Since JWST started returning data, paper after paper, dozens of them from teams all over the world that have flagged the same pattern. An impossible early galaxy problem, some call it. Galaxies that are too bright, too massive, too structured, too soon. And here's the part that makes this genuinely different from a lot of space headlines you've probably scrolled past. This isn't one weird outlier object that a single team found once and never confirmed. This is a pattern showing up across multiple independent surveys using different instruments, different teams, different techniques, all converging on the same uncomfortable question. So what's actually going on? Is Einstein wrong? Is dark matter wrong? Is the Big Bang timeline wrong? Or is something much less dramatic happening? A measurement problem? A modeling problem? Something earthly and boring hiding underneath something that looks cosmic and huge? That's what we're going to dig into. Not with hype. With the actual science, the actual disagreements between actual scientists, and the actual stakes if this turns out to be real. Because here's the thing. People don't tell you about a crisis like this. Even the scientists are split. Some think this is the beginning of a genuine crack in our understanding of the universe. Others think it's going to turn out to be a measurement artifact that gets them explained away within a few years. The same way plenty of universe-breaking discoveries have been explained away before. Both sides have real evidence. And by the end of this video, you're going to understand exactly why they disagree and what it would actually mean if the skeptics turn out to be wrong. Stick with me. This starts with light that's 13 billion years old, and it ends with a fight over the fundamental physics of everything. Let's get into it. Let's slow down and actually understand what JWST is doing, because that matters a lot for how seriously you should take any of this. JWST doesn't take a picture of a galaxy as it is now. It can't. Light takes time to travel. So when Webb looks at a galaxy that's, say, 13.4 billion light years away, it's not seeing that galaxy today. It's seeing light that left that galaxy 13.4 billion years ago, meaning we're looking at a snapshot of the universe when it was only a few hundred million years old. A baby picture of the cosmos, except the baby picture arrives late by 13 billion years. Now, how do astronomers know how far away, and therefore how far back in time, something is? Mostly through something called redshift. As the universe expands, light from distant objects gets stretched out, shifted toward the red end of the spectrum. The more the light is stretched, the farther away, and the further back in time the object is. Higher redshift number equals earlier universe. JWST was specifically built to be extremely good at this. It sees in infrared, which is exactly the wavelength that ancient stretched out starlight arrives in by the time it reaches us. That's the whole point of the telescope. It's a time machine tuned to the earliest chapters of cosmic history. So, when JWST started operating in 2022, one of its first jobs was to go looking for the earliest galaxies ever observed, pushing past what Hubble could see into redshifts of 10, 11, even higher. And it delivered. Spectroscopically confirmed galaxies at redshift 13, 14, meaning we're looking at objects from roughly 300 to 400 million years after the Big Bang. That alone was a huge deal. It pushed back the known record for earliest confirmed galaxy, again and again within just a couple of years. But the record-breaking distances weren't actually the most disruptive part. The disruptive part was mass, because a handful of these early galaxies weren't just far away, they were bright. Really bright. Brighter than expected for their age. And brightness, in this context, is a proxy for how many stars have already formed, which is a proxy for mass. In 2023, a team led by Ivo Labbé used JWST's infrared imaging to identify a population of red, massive galaxy candidates that appeared to have formed only about 600 million years after the Big Bang, with stellar masses exceeding 10 billion solar masses. That's the kind of number you'd expect from a galaxy that's had many billions of years to grow, not a few hundred million. Then, Boylan-Kolchin's analysis, published in Nature Astronomy, took 6 of the most extreme of these early massive candidates and ran the numbers against LCDM's own internal rules. The model doesn't just say matter clumps together over time, it makes quantitative predictions about how much matter should be available to form stars in a dark matter halo of a given size at a given point in cosmic history. There's an upper limit on how efficiently gas can convert into stars. Even with generous assumptions, you can only get so much stellar mass out of a halo that young. His finding? Several of these galaxies appear to need more stellar mass than their halos should reasonably be able to produce, even if you assume the maximum plausible efficiency, close to 100% of available baryonic matter converted directly into stars. Real galaxies, including nearby, well-studied ones like our own, Milky Way, typically converts somewhere around 20% of their available gas into stars over their whole lifetime. These JWST candidates were implying efficiencies that push toward the theoretical ceiling in a fraction of the time. That's the impossible part. Not that the galaxies are far away. That's expected and exciting, but not shocking. It's that they appear too massive, too fast, for the universe's gravity and available matter to have built them through the process LCDM describes. And this wasn't a one-paper phenomenon. Follow-up studies kept flagging the same tension from different angles. Some researchers looked at the sheer number of these bright early galaxies, not just their individual mass, but how many of them there are, and found there are more of them than standard models predict, by a significant factor. Others pointed out that many of these early galaxies look unexpectedly compact and structured, almost mature-looking, when the model expects something messier and more chaotic at that stage. Put it all together, and you get what several astronomers, including researchers building on earlier work by Christopher Consolis, Roger Frank, and Stacy McGaugh, have described as galaxies that appear too big, too bright, too early, too soon. The pattern shows up across brightness, mass, structure, and sheer abundance, not just one measurement in one paper. So by 2024 and into 2025, this has become one of the most actively debated open problems in observational cosmology. Not internet speculation. Actual peer-reviewed back and forth, actual conference. Talks, actual competing papers trying to explain the same dataset in different ways. Which brings us to the most important question. Does this mean Einstein, or dark matter, or the Big Bang itself, is wrong? Short answer, almost certainly not in the way clickbait headlines want you to think. But the longer answer is way more interesting than a yes or no, and that's what we're covering next. Here's where a lot of videos on this topic stop. They show you the impossible galaxy headline, they let you sit with the shock, and then they cut to a sponsor. We're not doing that, because the actual scientific fight over what this means is the best part of the story. Let's start with the most basic pushback. Are the masses even right? Determining a galaxy's mass from a JWST images isn't a direct measurement, it's an inference. Astronomers measure how bright the galaxy appears at different wavelengths, then use models of stellar populations to estimate how many stars and what kind of stars would produce that pattern of light. That process depends on assumptions, the age of the stars, their chemical composition, how much dust is dimming or reddening the light, and what's called the initial mass function. essentially the assumed mix of small and large stars a galaxy produces when it forms. Change those assumptions even a little, and the estimated mass can swing by a large factor. Some researchers argue that early galaxies might have systematically different star formation conditions than galaxies today. For example, forming unusually large numbers of massive, bright stars relative to smaller ones. If true, that alone could make these galaxies look far more massive than they actually are without breaking any physics at all. It would mean astronomers are slightly miscalibrated, not that the universe is broken. There's also the dust question. Dust doesn't just dim light, it reddens it, mimicking some of the same signatures astronomers use to identify very distant, very old stellar populations. A galaxy full of young stars wrapped in a lot of dust can, in some analyses, mimic the light signature of an old, massive galaxy. Get the dust modeling wrong, and you can accidentally manufacture an impossible galaxy out of a perfectly ordinary one. Then there's a more direct rebuttal, and it's a big one. In 2026, a team led by Francisco Prada used a massive cosmological simulation, the UU simulation, built from 2.1 trillion particles, run entirely within standard LCDM physics, to test whether the stellar mass-to-light ratios claimed for these ultra-early galaxies were even physically plausible. Their conclusion: for the universe to have produced galaxies as bright as claimed, at those redshifts, the stars would need to be shining with an efficiency that the physics of stellar evolution doesn't really allow. In other words, some of the most extreme mass estimates may simply be wrong, not because the galaxies aren't real or aren't early, but because the light-to-mass conversion used to estimate their size was too aggressive. And there's a third line of pushback that's arguably the most reassuring for mainstream cosmology: spectroscopic follow-up. Early. Galaxy candidates are often first identified photometrically, meaning based on their color and brightness in a handful of filters, which is fast but rough. Spectroscopy, splitting the light into a detailed rainbow and measuring exact features, is slower but far more reliable, and it can be a reality check on both the distance and the mass estimate. A 2024 JWST Fresco survey looked specifically at a sample of 36 massive galaxies with confirmed spectroscopic redshifts between Zeta 5 and Zeta 9, a slightly less extreme but still early cosmic era. The result? Most of these galaxies fit comfortably within what LCDM predicts. Only the very most extreme handful, 3 galaxies out of the sample, push towards star formation efficiencies of around 50%, which is unusually high but not physically impossible, and nowhere near the over 100% this literally cannot happen territory that the most dramatic headlines implied. That's an important nuance. This survey didn't find no problem at all. It found that the crisis shrinks significantly once you use more reliable measurements. From the entire population of early galaxies breaks physics, down to a small number of extreme outliers are still hard to explain. That's a very different, much more manageable scientific problem. So where does that leave us? Split, honestly. Some researchers think the impossible galaxy problem is real and points toward needing new physics, maybe modified early universe dynamics, maybe different dark matter behavior, maybe faster structure formation than LCDM currently allows. Boylan, Kolchin, and others in that camp argue the tension is genuine and won't fully disappear with better dust models alone. Other researchers think this is a classic case of extraordinary claims from early, uncertain data, and that, as measurements get better, mass estimates get revised downward, and the crisis quietly resolves into, early galaxies formed a bit more efficiently than we assumed, not the standard model of the universe is broken. Both groups are looking at the same telescope, the same raw data, and reaching different conclusions, because the disagreement isn't about what JWST saw, it's about how to correctly translate raw light into a number for how much mass is really there. That's the real frontier right now. And to be clear, nobody serious is claiming Einstein's general relativity itself has been falsified. What's actually being debated is much narrower, whether the rate at which structure formed in the very early universe matches what LCDM predicts. That's a real and fascinating scientific puzzle. It's also a much more precise, much less apocalyptic claim than physics is broken, which is why it rarely survives contact with a clickbait headline. Next, let's talk about what happens if the skeptics are wrong, and why this connects to another, even bigger crack physicists have been arguing about for over a decade. Let's play this out both ways, because both outcomes are genuinely interesting. Scenario 1, this resolves quietly. Better spectroscopy, better dust modeling, and refined stellar population assumptions bring the mass estimates for these early galaxies down into a range LCDM can comfortably explain. A few outlier objects remain unusual but not impossible, maybe explained by unusually efficient localized star formation, or rare dense pockets of early gas collapse. Cosmology's standard model survives, slightly bruised, mostly intact. This is, historically, how a lot of crisis claims in astrophysics have ended. Science is full of early results that looked earth-shattering and turned out to need one more round of better data. If you want a precedent for this, back when Hubble first started pushing into high redshifts, some early. Galaxy candidates also looked implausibly massive and mature, and many of those cases were later refined downward once spectroscopy caught up with photometry. It's a pattern the field has seen before. Scenario 2, it doesn't resolve, and it's real. If, even after every reasonable adjustment to dust, stellar, populations and measurement error, a meaningful population of galaxies still turns out to be too massive, too structured, and too early for LCDM's own math to produce. That's a genuinely big deal. Not Einstein is wrong big, but our model for how the early universe assembled matter into structure needs a real update big. That could mean several things, and this is where it gets genuinely exciting rather than scary. Maybe dark matter behaves slightly differently in the extremely early universe than assumed. Maybe star formation, in the first few hundred million years, was fundamentally different, faster, more efficient, less messy, than anything we see happening in galaxies today. Maybe there's a process that lets matter collapse into structure earlier than current models allow. None of those possibilities require throwing out relativity or the Big Bang. They'd require refining the details of how structure formed within that framework, which happens in cosmology fairly regularly. LCDM itself has been adjusted and refined multiple times since it became the standard model in the late 1990s. A revision here wouldn't be the collapse of physics. It would be physics doing exactly what it's supposed to do when new data doesn't fit the old model. And this connects to something else you may have heard of, the Hubble tension. That's a separate, well-established puzzle where two different methods of measuring how fast the universe is expanding, one based on the early universe's leftover light, the other based on nearby exploding stars, give answers that don't quite agree with each other at a level that's statistically hard to dismiss as pure error. It's been an open, actively studied problem for over a decade. And just like the early massive galaxy question, cosmologists are split on whether it points to new physics or a subtle measurement issue that hasn't been fully pinned down yet. The interesting thing is these two puzzles, the impossible early galaxies and the Hubble tension, are separate lines of evidence discovered through completely different methods. They don't have to be related. But some researchers have started asking, cautiously, whether they could be two symptoms of the same underlying gap in our model of the early universe. That's speculative. Nobody has proven a connection, but it's exactly the kind of question that keeps this field moving. So where does that leave you watching this today, on August 12th, 2026? Here's the honest state of play. JWST has genuinely found galaxies in the very early universe that look surprisingly massive, bright, and structured for their age. That's not clickbait. That's published, peer-reviewed, actively debated science coming from multiple independent teams. Whether that means our standard model needs revision or our measurement techniques need refinement is still an open, contested question among working cosmologists. Both explanations are on the table. Both have real evidence behind them. And the answer is being fought out right now, one paper, one survey, one spectroscopic follow-up at a time. That's not a smaller story than JWST broke Einstein. It's a more honest one, and honestly, a more interesting one because it's not over. Nobody knows how this ends yet. Not Boylan Colchin, not Prada, not the Fresco team, not anyone. That's what real, unresolved science actually looks like. Messy, contested, evidence-driven, and still being written in real time. If new data comes in, a fresh spectroscopic survey, a reanalysis using better dust models, a new batch of even earlier galaxy candidates, this story is going to move again. And when it does, that's worth covering accurately with the actual sources and the actual disagreement intact. That's the real story behind the headline, not manufactured drama. Actual, ongoing scientific uncertainty about how fast the universe learned to build things, which, if you think about it, might be even better than the version that gets clipped for 15 seconds and captioned, "Einstein was wrong." Thanks for watching. And if you want, I'll go deeper on the Hubble tension next, since that's the other half of this puzzle.